Today, we will be discussing genetic mapping as it pertains to linked loci on a single chromosome. For our example, we will be demonstrating how a lion's loci for eye, mane, and coat color genes can be located on the same chromosome, and how crossover events can affect progeny composition. Here is the genetic map for our lion chromosome, and it is indeed a diploid organism, so we have two alleles for each trait. And you can see here is our eye, mane, and coat color traits, and they are all linked on this one chromosome. We have the centromorgans separating them, 23.0 for our R1 and 16.0 for our R2. Over here in the corner is our coefficient of coincidence, 0.68. And so we've decided that blue eyes are dominant to green eyes, red mane is dominant to black mane, and the tan coat is dominant to the brown coat. And beside each of these separate alleles, I have them color-coded, so when we are looking at the chromosomes later, you'll be able to easily distinguish. Now we're going to briefly discuss the crosses that would lead to the genetic map we are observing above. So we're going to take a homozygous dominant female and cross her with a homozygous recessive male. Each of the genotypes are written out beside the loci on their respective chromosomes. Now this would yield an F1 of all heterozygous dominant progeny. They would all have blue eyes, red mane, and tan coats. So in order to determine which or what gametes this individual would produce, we would test cross them with a homozygous recessive individual. So their F2, the progeny of this cross, will all exhibit the phenotype of the gamete that they are receiving from this individual, because all of the other gametes from this individual will be recessive. I wanted to show this image very shortly just to give an idea of the duality of the crossover events. So here we have our no crossover event with our two parental gametes, and here we have our single crossover event. So this shows what would happen if we had a single crossover for either chromosome. So you have the big B, little r, little t, and the little b, big R, big T, and it kind of shows where that single crossover event would occur right here. And you can see the same for the single crossover event 2 right here, where we have our T's mixed up, and the double crossover event where they would kind of zigzag right here to give us these gametes. Here we have the 8 possible gametes produced by the heterozygous individual with their crossover event type, phenotype, and probability listed beside. Here we have one of the DCO events, the green-eyed, red-maned, and brown coat individual. To do this, you would just take the R1 and R2, the regions, and multiply them by the coefficient of coincidence. So 0.23 times 0.16 times 0.68 will give you 0.025, which is our double crossover event probability. But for this specific gamete, it would only get that half the time as you saw from our last video example. So it would actually only be 1.25% of the time you would actually observe this gamete. For our single crossover event 1, we have our green-eyed, red mane, tan coat, And for this, we would take the R1, the 0.23 centromorgans, and subtract that by our double crossover event probability, which is the 0.025. So 0.23 minus 0.025 gives us 0.205. Now, this is only the probability of the single crossover event, not the specific gamete. So we have to divide that by 2 again, and we will get 10.25%. That's the probability of observing this specific gamete.